Good day to everyone joining us, and welcome to today's XTalks webinar. Today's talk is entitled ATMP Manufacturing Processes Using Computer Simulation to Improve Operational Efficiency. My name is Sonia Hunt, and it's my pleasure to be your XTalks moderator for today. Today's webinar will run for approximately 60 minutes. This presentation includes a Q&A session with our speaker. This webinar is designed to be interactive, and webinars work best when you're involved. So please feel free to submit questions and comments for our speaker throughout the presentation by using the questions chat box, and we'll try to attend to your questions during the Q&A session. Now, this chat box is located in the control panel, and that's found on the right-hand side of your screen. If you require assistance, please contact me at any time by sending me a message using that chat panel. At this time, all participants are in listen-only mode. Please note that this event will be recorded and made available to you for future streaming on xtalks.com. At this point, I'd like to thank Genesis AEC, who developed the content for this presentation. Since their inception, Genesis AEC, an award-winning architecture, engineering, and construction firm, has helped life sciences companies usher in the next generation of life-saving therapies, treatments, and technologies. Whether it's providing AE support for existing sites, commissioning, validation, and qualification for specific processes or equipment, or turnkey design-build solutions, their team blends sound science and technical expertise with quality and safety to deliver unparalleled results. Now it's my pleasure to introduce you to our speaker for today's webinar, and he is Steve Hall, Chief Process Engineer with Genesis AEC. And there he is. Steve has over 40 years of experience combining business understanding with technical expertise to deliver capital projects and services with exceptional value, speed, and compliance. Steve is recognized internationally as an expert on process engineering for upstream manufacturing facilities, including small and large molecule APIs, critical utilities, CIP systems, and material transfer. His book, Rules of Thumb for Chemical Engineers, 6th edition, is a highly regarded handbook for process and project engineers. His engineering software is used globally for sizing pipelines and designing heat transfer systems. Now it's my pleasure to pass the mic and the controls over to Steve. So Steve, when you're ready, you may begin.
Thank you, Sonia. It's my pleasure to be here today. We're going to talk today about ATMPs and simulation. Just get my screen started.
Yep, we can see your screen.
Thank you. ATMPs, advanced technology manufacturing processes, are used in the industry today. It's the really hot topic for doing viral vectors, plasmid DNA, for cell therapy and gene therapy products. And many of these manufacturing sites utilize similar technologies, being bioreactors or fermenters, TFF skids, chromatography columns, filling, packaging. And they utilize a lot of resources that are often single use and discrete, such as buffer containers and media. What we're going to talk about today are some tools that we use at Genesis to model these processes in the plants that can help save time by reducing the rework in the design, save money by optimizing the facility design, and provide information that would inform the cost of goods analysis. Before we get started, we have a few questions, one question actually to ask. And Sonia, perhaps you'd like to execute the poll.
Oh, certainly, I will do that right away. Okay, audience members, here's our first poll question, and you should see it appear on your screen. I'll give you 40 seconds to complete this simple poll question. What do you think are the primary reasons for performing a simulation of an ATMP process? Is it to determine the annual number of product batches? Or is it optimize the number of bioreactors and other equipment? Is it estimate resource consumption, i.e. single-use bags and WFI? Or is it predict staffing needs or don't know? So please go ahead and cast your vote. And then I will close the polls and we'll take a look at the results and get right back to the presentation. Okay, Steve, that looks like we have the majority of our audience members have cast their votes. I'm going to leave it open just for a few more seconds so we get everyone involved. Perfect. That looks like it's everyone. Thank you so much, everyone, for participating in our poll question. I'm now going to close the polls and let's take a look at the results. Okay, so here are the results. So in our audience, we have 38% that said determine the annual number of product batches. Then 13% said optimize the number of bioreactors and other equipment, while 25% of our audience, Steve, said estimated resource consumption for single-use bags and WFI. And then we had 0% that said predict staffing needs, while 25% said they don't know. So thank you, everyone, for participating in that poll question. Now, Steve, before you continue with your presentation, I'm curious, what are your thoughts on the results of that poll question?
Well, it's really interesting, Sonia, because the two case studies I'm going to show address the two highest poll results. One, predicting or helping to estimate the number of batches that can be achieved in a facility, and the second being resource utilization. So,
okay.
Right, I cannot actually see the polls on my screen for some reason, but.
Oh, did you want to see that? Do you want me to tell you the results of, are you okay?
I
Okay.
got it. Good.
All right.
Learning topics. Before we get into the case studies, I do want to talk about the different types of modeling and simulations. So there's a few slides that have definitions on them. We'll just go through those relatively briefly. Secondly, a few slides about the types of outputs that we can get out of these simulations. Next, matching those inputs and what do you need to provide to a simulation for it to run effectively and to give you the results that you're looking for. And then we'll get into the two case studies. Please post questions in the chat as we go, if you have any. And if there's any really burning question, you could, I don't know, put it in all caps and Sonia will interrupt me. So what is a simulation? It means different things to different people, but the underlying thing about a computer simulation is that it's a set of algorithms, it's a set of calculations that a computer executes to try to model or replicate how an actual facility will run. You have to remember that it is an algorithm, it is a set of calculations, they're not exact. But with a well-designed simulation, you can tease out answers to many questions and understand nuances about the facility that you might not have understood prior to making it. A simulation is distinct from a model in that a simulation transforms a singular description of a unit operation and adds a time dimension to that. So we put models of plants into a timeline and run that to make a simulation. It's a again, a time-based picture of how a facility might look. And there are two primary terms here that are really important to understand. First, deterministic, second, stochastic. In a deterministic simulation or model, the underlying algorithm takes all of those inputs, crunches the numbers, and provides an output that'll be the same every time you run that simulation. Every time you run that model, you'll get the exact same results. I'm going to explain how that might be a good thing or a bad thing in when we look at the output slides. In a stochastic model, every time you run the simulation, certain of the inputs are varied. It's called stochastic, or often called a Monte Carlo simulation, because it has an element of gambling, of rolling the dice. Each time that you roll those dice, you get a different set of inputs. Only the inputs that you've defined as being randomized. And then that creates possibly different outcomes. And by running the simulation many times, maybe 100 times, you get a range of results that help understand what let's say the design envelope may be. If you were to use a deterministic simulation and calculate the water consumption, let's say, for a day, and then you run that simulation 100 times, you're going to get the same estimate of the water consumption for each day. But if you ran it stochastically, where the water consumption was varied based on whatever randomized variables you determined that could change that, you would get a range of water consumption so that you could understand better. It's not an average of 1,000 liters an hour. It's a range of, say, 500 to 1,200 with an average of 1,000. So many of the days much less, a few days a little bit more, and that gives you the average. And then last slide on the definitions of simulation are these three types: batch, continuous, and discrete. We've got simple examples for each. In a batch simulation, you are processing a fixed quantity of material. Oftentimes it's in a tank, so in a bioreactor, for example, or a fermenter. And the simulation or the model looks at the progression of that batch that's in the tank from its beginning to the end. So you can have a heat up, a cool down, a cell growth during the batch, and track parameters associated with that along the batch length. But at the end of the day, you have a batch of material, one bulk. On the other hand, a continuous process usually has an input and an output that they can vary over the course of your simulation time frame, but the total quantity of material that's processed varies over time. My example here is wastewater neutralization. A lot of our facilities have this, or they have a biogill system. And the wastewater that goes into that system, the flow rate can change, the quantity per hour can change, but what happens in that unit operation itself is that you're getting an input, you're processing it as it comes, and then it overflows out. That's a continuous process. And the third type is discrete. And these are often characterized by packets of material that go through and step through a facility, like vials, or in my example, drums of buffer. Discrete simulations help define the amount of space that's needed to store the material, the throughput, how many barrels get filled each day or emptied each day, the time that things are waiting. And in my second example, we're going to see a little bit of that. Simulations can combine all three elements, but it depends on the software and the designer as to how effectively that's done. Some simulation programs are really geared to a specific one of these, like FlexSim is one you may have heard of. It's a discrete simulation package. So to get information out of a simulation. Again, it's a computer model, and very often it's going to create tabular data. That tabular data could be pretty immense. I've done simulations that have created tables with 50 to 100,000 rows in Excel. And diving into that quantity of data can be a pretty daunting task. The example on the screen is not very readable even because it's actually a relational database, and the numbers that are in the columns that refer to other tables where the definitions of those values actually lie. So we look at visualization tools instead to really present most of the results, or statistical tools against the tables where we might calculate means, averages, maxes, minimums, standard deviations, that sort of thing. But here, looking at Gantt charts, you've probably seen these. Gantt charts are time-based bars that show activity in the steps that are listed down the left-hand side. So these could be pieces of equipment, they could be tasks, they could be schedule activities. So Microsoft Project uses a Gantt chart to show a schedule. We use them for depicting the operation of our facilities in our models. And when I said that stochastic simulations can be useful, when you look at the one on the left, you can see that each of those sets of bars, which represent different batches, are identical or nearly identical. They have the same time periods. They start and stop at the same times. In real life, things aren't so predictable, and some of the time frames are going to be elongated. There can be unexpected stoppages for QC, or maybe the schedules of workers could change when individual tasks can start. So what the stochastic model would look like is perhaps a more staggering of those Gantt bars. If you receive a Gantt chart output from your modeler, and every batch looks identical, and they're marching with precise start times, 8:30 every morning the batch starts, that kind of thing, I would question that and start drilling in to find out, why aren't we seeing some variation here. Next kind of chart, well, various graphs. We've got pie charts, just scatter charts, and histograms on this page, and any other kind of graph that you can think of. So the one on the left is a pie chart that shows the OEE, or the operational effectiveness and efficiency of equipment, and it breaks down the utilization of that equipment by idle time, as well as production time and stoppages and QA, QC, and maintenance. The one in the middle is simply a scatter chart that shows by the hour usages, in this case of by a safety cabinet in a small additions lab, prep lab. And I've got more examples of that coming up. And the last one is a histogram. Histograms are column charts, as you can see, but what they do is count how many instances occur within different ranges. So in this one, this was talking about weighments, API weighments, and the values on the x-axis are ranges of weighings. So from 0 to 0.5 kilograms, 0.5 to 1, 1 to 5. And then over the course of the time frame that this was done for, how many Wayments fell into those different categories or those ranges. And why this is interesting is that you can use it to help understand what size containers would I be weighing into? How big should the scales be? How much activity am I going to be getting on a large capacity scale versus small activity scale? Things of that nature. You might be impressed with animations. This one is typical of what you might see out of FlexSim or some other discrete simulator. And they are really fun and they're fun to look at. But in my mind, they're a lot of work to create, and they don't really give the kind of value or feedback that you need to do the optimizations that we're looking for. They might help a little with a time and motion study, but I think you get better, more actionable information out of charts, graphs, and Gantt charts, tables of information that you statistically evaluate rather than fancy animations. Not going to talk about them anymore. So what are we doing here? Taking things that I call recipes, which are step-by-step activities to do a task or an operation, putting those together into a plan, and then running that plan through a simulation engine, the set of algorithms to get the results. And those recipes can be informed by resource restrictions and other options such as calendars and people and facilities. We like to start our ATMP simulations with flow diagrams. Simple flow diagrams like these are block diagrams. They don't show details like you'd see on a PFD or P&ID. These are blocks that show the unit operations that make up the process. And importantly, in most cases, we're going to want to understand the inputs and outputs from these blocks. And if we can, assign those to timeframes. So you can see on these examples, there are timeframes, there are inputs, there are outputs, some of them are calculated. And these can be transformed directly into process simulations. We're also going to be looking for the various resources, fixed and variable resources that we want to utilize in the simulation. Now, we only need to know those for the things that we're interested in getting into the outputs, which is why we really talk about outputs first and then discuss what inputs are needed to obtain those. We can have different calendars, different consumables that are, consumables might be consumed on a per use basis, like every time you charge the bioreactor, you're going to use 200 liters of media, or they could be consumed on a usage basis, utilization like people, labor could be 1 person per hour. So if the task takes 4 hours, you've got 4 person hours versus if the same task was only 1 hour, you'd only have 1 person hour. So a couple of different ways to look at consumables. And then calendars, this example here has 4 different calendars, and these calendars show the time of day that tasks are allowed to begin. And we can assign any calendar to any task, so that certain tasks maybe are 24/7, certain activities, they don't wait for the clock, they just go on, but others, and you'll see an example, maybe there's only the day shift that takes care of it. So when it gets to that point in a recipe, that recipe might pause until the day shift arrives. Okay, first example, case study, it's called production capacity. We wanted to estimate how many batches per month this cell therapy or gene therapy facility could make. There's also a viral vector in this facility. This one also wanted to track bin movements. So we see on the screen block diagram is just a snip from the project documents that shows the chromatography steps and TFF, 4 steps. And in the middle is the same 4 steps, but this time characterized with single-use bins of buffer that were used to feed the Chrome systems. And the little yellow lines vertical are time bars, days. So with this information, then there's a lot of, probably could read it in the handout, are the assumptions that went into this. So with this information, this is what we reviewed with our client to level set what inputs we might, that we're going to use, and talk about the outputs to come from this. Come to agreement on that, and then we went away, did the simulation, came back, did a few iterations because the simulations always generate additional questions that we want to address. So here's a recipe, a piece of one, and it lists, as I said, steps. We're looking for the use of the single-use containers. So these are these sub 65s, 65s are subroutines that go to other recipes. And step through it, there's predecessor relationships, time durations for each of these different calendars that are called for. And then these different tote values, this is all customizable, but configurable, I should say. These track the single-use containers in the facility. So there's pluses and minuses as they appear and disappear in different locations for the recipe. This is the subroutine for the buffer. And then take those and assemble them in a plan. So the plan, you can see the recipe numbers, there's a lot of them, and this is just a snip from the overall plan that we created for this project. Each of these recipes were assembled into what could look like a production plan that you put into your facility with predecessor relationships, and these can have their own individual calendars if we wanted to override the ones that are built into the individual recipes. The dates and times that are over here, this is actually after the output, and this is what it came up with for starting and stopping each of these recipes. And there's a much more detailed table that shows every step in every recipe placed into a master list with these dates and resource utilizations. Created the Gantt chart. You can see those tasks were already there. The recipe steps pointed to pieces of equipment for each step. So those are listed here on the left. And then the time durations of those. And then they're just charted out here. The colors refer to different batches. We can color these in pretty much however you can imagine it based on the information that's available. So they could be color coded by task, if we assign task names to the recipe steps, such as cleaning or production or idle. And with this Gantt chart, we can see that some of these steps look like they're running back to back to back, which is true. And so that tells us that we're pretty close to the critical path for running this process in with this set of recipes with the assumptions that are in there. And we can just back up, look at a more complete Gantt chart, and just count off, or the computer counts off, how many batches are completed within the time frame. And now we know what the optimal production capacity is, nominal production capacity, I really should say. It also is counting the various tote positions, as I showed. And this is daily transfers from one to another. And consumptions, it was adding up in the recipes. Here's water that's used, here's buffer, here's media at each of the steps in the recipes, and it adds those up on a daily basis. But it can also add up on an hourly basis. So here, hourly, we can see there's quite a lot of variation. Now, this says sums in use in the small addition solution prep room, and there's a pretty high number at the peak. But here's where interpretation and product knowledge comes into play. Because pretty clearly, when you're making small additions for media prep, you can level set the usage of the equipment. So we take some of these outputs with a grain of salt and apply engineering judgment. We might do some averaging here and say, well, really, you don't need, what's the big number on there, 30, maybe 8 to 10 would be more reasonable. And this is a facility with 8 large cell processing rooms. So that doesn't seem unreasonable at all. Second case study is sample management. In this case, we have a client that's doing a monoclonal antibody, and they start with apheresis and bring in samples from their patients and run it through a process. Their plan was to expand their throughput by about 20% in an existing facility. And they were concerned that they might not have enough analytical capability to handle the additional load. So we have we had a couple of different processes that generated the samples. And this is just an example from one of them. And what we asked them for was a block diagram with the description of the steps and timing, and then what samples came out of those steps. So that's what they gave us. And then we looked at those samples and looked at the block diagram, and we created a simulation around it. We started with a basis, how many batches per week were they going for? And we talked about the variability, because even though this 92, if you divide that by 7, you might get around 12 or 13 batches a day. We know that they don't actually do exactly that every day. The samples, the patients come in on a more randomized basis, and maybe fewer on Saturday and Sunday than on weekdays. So after discussing that and looking at different models for randomizing the start times for these batches, we came up with a model. And similarly, on the time it takes to process a patient's cells, that varies over a time period. So we talked about that. We created a sample matrix that stated for each of the samples, you might have noticed they were labeled D001, et cetera. What happens to those samples? Do they get processed in right at the line, or are they taken to the sample accessioning lab? And if they're in the sample accessioning lab, are they divided up? Do they get processed further? before sending them on to analytical, or maybe they're sent directly to storage for retains. And they fell into those kinds of categories. So we characterized all of that, and then did the simulation over a course of time, ran this many times, and basically we're able to count and show, well, here's the range of numbers of batch starts per day that our model was predicting. And here's how long the batches lasted. This is a histogram. So between, most of them were here between 8 and 9 days, but a few are shorter and a few are longer. That's important because the samples pop out at defined points in the process, not at time points, but at process points. Then we counted the sample accessioning. This is by day, how many samples actually would be going to the accessioning lab. And then next to samples accession by hour. And this is the one where you can see all these peaks. This is 8 o'clock in the morning in our model because there's no sampling overnight. And we were able to talk about that. How many go to storage? So overall, in summary, I want to emphasize that you should know what you want to learn from your simulation before you get started. I want to emphasize that there's a real benefit to doing stochastic simulations. And finally, modeling is an art. There's interpretation that needs to be done. It's not the actual process that's running. It's an algorithm and a mathematical model. We have another poll that Sonia is going to conduct here, and then we'll go into Q&A.
Well, thank you very much, Steve, for that great presentation. I hope everyone enjoyed it. And now we're going to do our final poll question. So I'm going to launch it now. And there you go, everyone. Okay, so the question that we have for you is, how would you use simulation tools in your role? So check all that apply. So you have a couple options below, which is using Excel as a tool for modeling your process, or is it applying shrink wrap simulation software? The next one is estimating cost of goods for an existing proposed product, or is it designing a new or renovated facility? So please go ahead and cast your vote. Just like before, we'll take a look at the results once I close the polls, and then we'll get right into the Q&A. And just a reminder to our audience members to continue to send in your questions by using that questions window that's located on the right-hand side of your screen, and we'll try to attend to all your questions during the time we have together for the Q&A. Okay, it looks like that is the majority of our audience members have cast their vote, so I'm now going to close the polls, and let's take a look at the results. Okay, so in our audience, Steve, we have 67% said using Excel as a tool for modeling your process, while 11% said applying shrink-wrapped simulation software. Then we have another 11% saying estimating cost of goods for an existing proposal product, or 56% saying designing a new or renovated facility. So thank you everyone for participating in our final poll question there. And now, before we get into the Q&A, I'll ask Steve to put on his webcam and I'll put on mine. And then you can unmute yourself there, Steve. Okay, perfect. All right, now before we get into the Q&A, Steve, I am very curious to find out what your thoughts are on the results of that poll question. Are you surprised?
I was most interested to hear what people thought about shrink-wrapped software versus Excel. So it heartens me to see the Excel aficionados there.
Okay, thank you so much for that comment there, Steve. Okay, so let's get into our Q&A portion of the webinar. Okay, we've got a couple questions coming in. So while you're speaking, I'll tend to those ones first, and then we'll get to these questions here that are coming in. So this audience member here asked, When is it appropriate to run a deterministic model versus a stochastic model? That's a good question.
Yeah, so that's a good question. I really did emphasize the importance or interest in running stochastic models. But before you just start running it stochastically, it really helps to do it deterministically without changing the inputs to help debug the model. So a lot of times we'll run it with a fixed set of inputs to debug it, and then follow that with starting to vary different elements. And also, kind of like a design of experiments, you can vary different inputs individually to see how that affects. It's a way to find what your design space is and which of the inputs have the most effect on those outputs.
Okay, thank you so much for that, Steve. Let's go to our next question. This audience member is asking, what types of parameters can you change for the Monte Carlo simulation? Different shape distributions?
Right, so really the sky's the limit. We do everything from a normal distribution to various shapes, Gaussian, exponential. So those are statistical variations. But you can also, interestingly, create your own histogram or table of probabilities. So you might want to have some really odd-shaped distribution, or you might, which you apply a random number to. So it could be a step shape, or it could be some other shape of input values. So each time, and when I say shape, what I mean is if you have an input of, let's say, time, and that time is going to be 1 hour to 2 hours. And in that 1 to 2 hours, when you run that simulation 10 times, would it be, and then you plotted how many, like more than 2/3 might be at 1.5 hours, you might have one of each at close to 1 and close to 2, that kind of a shape. So you could have a straight shape, it could be completely random across the 1 to 2 hours, it could be a bell-shaped curve, it could be a slant, whatever kind of shape is reasonable for your process.
Okay, thank you so much for that detailed answer there, Steve. I'm not sure if we're able to do this one here, but this audience member is asking, could you show us again the multicolor histogram slide? Which slide is that? Or do you want me to pass you back the controls, or do you want me to go to it?
The multicolored histogram slide. Oh, yeah.
Pass you back the controls?
That's the one just before animation.
And how many slides? Do you want me to pass you the controls, or do you want me to go to it?
You can go to it. It's slide 12.
Okay, so keep on going.
Yeah, that's it. You're at 28. That's 30. Go to 12.
Oh, 12. Okay, all the way up here.
There, that's it.
That's one. Okay.
No, that's 15. That one. No. Oh, you have different numbers than me.
Yeah.
Goes forward. 15, 16. Keep going, keep going, keep going, keep going. One more. One more. That one.
That one. Okay, we did
No,
it.
before this.
Oh, before this one?
Yeah. What's the question?
Okay, so the question was, could you show us again the multicolor histogram slide, please, in a little more detail about it?
So in a histogram, what you're looking at are the frequencies in different ranges. Let me just stare at my screen here. This one is API Waymans. It's called API Waymans.
Mm-hmm.
So in this particular simulation, over the simulated time period, there were weighings that were occurring in the simulation. And those weighings of raw materials, APIs in this case, were the amount that was weighed out was calculated by the simulation. And it added up how many of the weighings were in the range of 0 to 0.5 kilograms, how many were from 0.5 to 1, from 1 to 5, 5 to 10, 10 to 25. So in a histogram, they don't have to be equal distances. They can be, different ranges, which this one is. So it actually just counts how many times during the course of all of these hundreds of weighments, there were, the left-hand one, the tall red bar, 750. So there's close to 2,000 times something was weighed out in this simulation. 750 of them were between 0 and 0.5 kilograms. 500 of them were between 25 and 50 kilograms. So that's what it is. And so what do you do with that information? It was important on this project because we wanted to know how big the bins, how many bins of these different sizes we needed to plan for. But you can use histograms for all kinds of things where you've got a variable amount of stuff coming in. And we color coded this just to make it easy to understand for a presentation.
Okay, thank you so much. And I think we have here, and I think they wanted to know about this other histogram here. I'm just looking to see is this the correct one here? No, okay. I think you can probably answer that offline. For that audience member that was asking about the other histogram, I will provide an email address so that you can actually send it directly to Steve to answer. Okay. All right, then, Steve. Well, that looks like it's all the questions that we have right now. So I want to say thank you very much, everyone, for sending in your questions. We have reached the end of the Q&A portion of the webinar. If we couldn't attend to your questions, the team at Genesis AEC will follow up with you after this presentation. And if you have any further questions, please direct them to the email address that's on your screen. And there's also a website there that you can also check out. And we'll talk a little about that in a second. So thank you, everyone, for participating in today's webinar. You will be receiving a follow-up email from XTalks with access to the recorded archive of this event. A survey window will be popping up on your screen. Your participation is appreciated as it will help us to improve on our further webinars. Now, give me a few seconds. I'm about to send you a link in your chat box, and you'll be able to view the recording of this event with this link, and also share this link with your colleagues so that they can enjoy the presentation as well. So I encourage you to do that. And get even more out of today's presentation by downloading the supporting material that is available under the Handouts tab, and we do have a PDF of this presentation for you. So please go ahead and check that out. Now, please join us in thanking our speaker, Steve, for that very insightful presentation. And Steve, before we head out, I just wanted to comment, if you're interested in learning more about modeling and simulation, please visit Steve's website where you can read his series on simulation as well as access additional resources. So it's right here on this, right here is where you can find all that information out. Okay, we hope you found this webinar informative. It has been my pleasure to be your webinar moderator. On behalf of the team here at XTalks, we thank you for joining us. Until then, I'm Sonia Hunt. Take care and bye for now. Thank you again, Steve. Thank you, everyone.
Thank you, Sonia. Thank you,
Okay.
everybody.
All right, bye-bye.